Okay, today we're going to be working on 4.5, where we're going to be modeling exponential and logarithmic functions, growth and decay models. Let's just focus on this thing right here. This is our basic structure for our exponential growth and decay functions. We're going to use E as our base for our growth, and then K will be a rate of growth, and T will be the time. K is not specifically like a direct rate of growth. It's on its exponential scale with E. So we're thinking like if it's positive, we know it'll be going up. If it's negative, we know it'll be decaying. But it won't be exactly a percent, but it is a rate of growth. A naught, this is the original starting value. So think of it a little like principal, what you put in the account. A is what you end up with as a result. K is, of course, some sort of a rate, and T is the time we leave it in there, usually in years. When K is greater than 0, it'll be an increasing or growth model, and we'll see that it comes up like this, continuing to grow. And when K is less than 0, meaning negative, we'll see this decay structure, this decay function. So an example on page 419 talks about minimum wage and the change or growth in minimum wage. In 1970, we're told that the minimum wage was $1.60. Think about that for a minute. In 2000, it was $5.15. And we want to use substitution to figure out what this equation is. Now, this right here, this is really what we want to leave as a variable when we're done, because we want to be able to plug in any amount of time, so that's our other variable. These two should be left in the equation when we're done. We might substitute for them now, but in the long term, we're expecting to put them back as variables. The things that we need to know are the initial and this K. K tends to be the issue that we really have to work at. A naught's, obviously 1970, so it'd be 160. Okay, that'd be our initial value. It's what's K, and if we plug in the new, which is 515, and the time, which is 30 years, we should be able to solve for K. That's really our biggest issue here. So let's do that. We're going to go 5.15 equals 1.60 e to the k times t, but t is 30. Now this goes to what we did last time where we solved exponential functions. The e is the base and k times 30 is our exponent. This 160 doesn't matter as far as the exponential is concerned, so let's get rid of it. We'll divide by 1.60, and in our calculator, if we take 515 divided by 160, we get 3.219 will equal e to the 30k, and that'll work for us. Now what we want to do is we want to change this exponential to a logarithm, and because it's base e, we'll use an ln. That allows us to use the base e, and we know that all logs equal the exponent, so that's 30k, and over here we have 3.219. Well, I can take the ln of 3.219 pretty easily. Ln of, and I'm just going to use the answer key here to get as exact an answer as I can. I get 1.169 equals 30k, and so I divide by 30, and k will come out as divide by 30. Comes out as a 0.039. So we're going to say it's 0.039. So my equation is actually going to be A equals 1.6 e to the 0.039 t. So there's our equation that we've just built, and we might be interested in knowing what would the model say about today, our time. So if we use 2017, that would be 47 years. So I'm going to go ahead and use 47 as my exponent here. 1.6 e to the 0.039 times 47. And if we hit enter, we get $10. Now that tells me right now that something happened to the minimum wage values and the expected values since 1970. We could talk about the recession. We could talk about the impact of those things. I think that if we had not had the recession in 2008, 2009, 2010, if we had not had that problem in those time frames, I think that we would be able to see a number much closer to $10. But things like the recession happened. There was also a recession in the 80s. Those type of time frames can drastically impact the increase in minimum wage. But we expected the 80s to be involved in the equation. What was strange was, we wouldn't have been able to predict the problems in 2008 into this model. So that's what happened there. The next example we want to look at is on page 422. It talks about the Dead Sea Scrolls. They use carbon-14 dating to decide how old they are. But a lot of that has to do with the decay rate. And so we're going to look at the information we're given. It says that after 715 years, have passed, that the carbon dating will have decayed to half the original. 1/2 of the original will be left, meaning that A will equal 1/2 of A naught. That's important for us to understand when we talk about this half or a third, those types of things. So if we use our model, A equals A naught E to the KT, we don't actually know what A or what A naught is, but we do know that instead of writing A here, I can write 1/2 A naught equals A naught E to the K times 5,715. The reason we like this is now my next step would be to divide by A naught, and these cancel. So now I have 1/2 equals E to the 5,715K. And this is again a logarithm that I can work with. The ln base E of 1/2 will equal the exponent 5,715K. All I have left to do is divide by 5,715 and I will know what K is. So I'm going to go to my calculator. I'm going to take the ln of 0.5. It's negative, and now I'm going to divide that by 5,715 to get negative 1.21 E negative 4. Now that E negative 4 is the scientific notation from the calculator, which means to move the decimal 4 places left. 1, 2, 3, 4. Meaning I would have negative 0.000121 for K. That's a very small number, but these decay rates, this is radioactive decay, carbon-14, and so we now have a model that says the amount we have left of carbon-14 is the initial amount times E to the negative 0.000121 T. So we've built ourselves a model, and if we wanted to go back and find, hey, what would it be for different time frames, or at what point would we have different percentages, just like we used 1/2, we can do the same thing here. What's really nice here is if it was, say, 75%, because I would do 0.75 of A naught, the A naught will always cancel, meaning I just have 0.00121 T. As soon as I know what percentage I want left, I can use that decimal for the percentage equal to E to the exponent, and it works really well with the natural log pretty easily there. On page 423, we talk about a logistic growth model, and these growth models are a little bit harder to work with as far as their equation. The equation is that the amount left will equal C over 1 plus A times E to the negative BT. Now the way these work graphically, and why these are so interesting, is that if you were to look at a model, a graph of the model, you would see the equation taking off very fast, exponential growth, definitely. And then there'd be a point at which you would see the demands or the access to resources or whatever it is that's causing the growth to slow, you would see it inflect and flatten out. So it has an exponential growth followed by a decay. Okay, and there will be this top value that we're going to approach but never quite reach. And as we get that closer and closer, okay, this value here will be C. So whatever goes up here, that is our peak or max value. And so as we go through and look at these models of logistic growth, we'll see the spike followed by the decay. A great example of this might be a rabbit population. You know, you put them on an area where there's not any predators, and their growth is going to take off really fast. But then, as they run out of resources and food, you'll see their growth die off, and it will level off at a specific value that is sort of the optimum population for a group. And so we can work with that model in class, and we'll take a peek at it as we go through a couple examples there in class. All right, good luck, and we'll see you in class.